Okay?
Yeah,
You look very serious.
I'm just thinking a lot, right?
Okay. Okay, not yesterday, the day before yesterday, and we talk about on how to calculate the J, okay? So how to calculate the J? So here is a d pi dA. You can see J equals minus d pi dA. So you guys still remember? So J equals minus negative d pi dA, and based on the definition of d pi dA we have here, right? Okay. So we just denote this equation as a star, equation star. And then we have this derivation. This derivation, and we want the reason is that we want to show so this guy equals this guy. Okay? So I'm going to show you guys why we do this kind of derivation. So this is the boundary. This is a Ti, and this is dui. And dA, ds, and we get this conclusion. So dw and dA and capital D capital A. So we get it here. And when we do this, because for our original equation star, so this is original equation star. You can see guys, original equation star. We have 1, 2, 3, 4, 4 terms, right? Look at guys. We have 4 terms. 1, 2, 3, 4. And to simplify this, we do this derivation. And finally, we found that Ti, dui, dA, ds, this integration equals this integration. That means this guy, look at me. This guy equals this. Right? That means so this equation can be simplified as only this one and this one. So that's the reason we did the following derivation. So here we're going to have, originally we have 4 terms, 1, 2, 3, 4, 4 terms. But now we can only have 2 terms, right? So this is a simplification. Do you guys agree?
Yes.
So this is minus j. So we can, we will use this minus j equals this. And we will use this equation in the following these lectures, and I'm going to show you for any given problem on how to use this equation and to get this is a J integral. You understand this? So last time, maybe you have you are concerned, you are confused about why we do this kind of things. The reason is that we want to simplify this equation star from 4 terms to 2 terms, right? Okay, so this is what we talked about yesterday, and then we talk about the HRR. This is a function, and you know that. Okay, so I will not ask you guys to derive these equations, but you should know for these equations and what is singular and what is non-singular, and then why it is non-singular. So this is pretty much what we talked about last time. And today we are going to talk about the new things. So today we talk about lecture 14, and we have, so we are going to show you how to do this kind of calculation. How to do this calculation here, okay? So this equation, keep in mind, this is equation J, and J, this is what we have derived, right? So J equals, this is gamma, and this gamma is arbitrary. This gamma can be a circle, can be rectangular, can be hexagonal, or can be any kind of, this is the gamma. Okay? You understand, guys? As long as this gamma encloses and is the correct tape. For this case, so this gamma does not include the correct surface. And suppose this is a sharp correct surface. This is sharp for visualization. And I just draw this one very, very big, but and you just think this is very, very short. Okay? Otherwise, the J integral is not accurate. And so for here, we can see, so in this equation, the omega, here is omega. Omega is the shear energy density, and the W is work done by external forces. Here, we do not have work done by the external forces. We have traction Ti. So here, this is a crack tape, okay? Crack tape, and we have an X and a Y. And so this is, and we also know that, and the height is 2h. The height of this is 2h, and then this is a semi-infinite crack. We think this is a semi-infinite crack in an infinite body of 2h. 2h, okay? So this is the 2h. The height is 2h, and subjected to uniform U0. And you have U0, you have U0 on bottom, on top and about bottom. So this is U0, this is U0. And we are asked to get J based on this integral integration. And how to do that, guys? And we just how to do that? We just follow so this is equation, okay? You understand, guys? And first we draw, as you can see, and we draw enclosed curve. And for this curve, and for simplicity, I just draw this vertical, horizontal, and vertical, horizontal, and then vertical. I have on 5 segments here. 1, 2, 3, 4, 5. Right? You understand, guys? So I told you guys, so this is arbitrary. And the selection of this is the gamma. This is boundary. Is arbitrary. You can select circle, you can select rectangle, you can select hexagonal, as long as your gamma encloses the rectangle. Alright? So for simplicity, I just select vertical line and horizontal lines. So you can see, okay. So for the second one, for second boundary, for second light segment, and fourth the segment, and we know that. So this is X, this is Y. We know that, and for both of these two guys, the dy equals 0. Y does not change, right? So this is what we are told, and dy equals 0, and also, and this is the ui, okay. U, the displacement, you can see we have displacement here. The displacement has nothing to do with X. Right? The displacement has nothing to do with X. As a result, dui dx equals 0. This is infinitely long. This is infinitely long. Are you guys okay? I think you are confused. Am I right? Bobby, are you okay, Bobby? Yeah, one more time, okay? So when dy equals 0, for this line and this line, y does not change. Y does not change with respect to x. Right? Because you just pull it u0 and pull it u0, then fix it. U0 is fixed, u0 fixed on top and on bottom. So u0 does not change. Right? As a result, this y equals 0. And also the displacement u in y direction, the displacement u2, which equals u0 here, it does not change with x. Because it is infinite. And u1, I just assume u1 equals 0 in x direction. So as a result, for segment 2 and segment 4, dy equals 0 and dui dx equals 0. You understand? As a result, for j, okay, j is I have 1, 2, 3, 4, 5 segments. So because the integrand for second one and fifth one are equal to 0, as a result, I only have 1, 2, 3. I only have these 3 the integration in the integrals. You understand, guys? Okay, and then we can just look at the first segment and the fifth segment. And when we see this first segment and fifth segment, and what equation we can get, and we know this is edge, so this edge ui equals 0. Do you agree? ui equals 0. It does not move. Does not move in x direction, does not move in y direction for any given point. So sigma ij equals 0. There is no traction. Okay? If sigma ij is non-zero, that means there is traction, which is contradictory to the condition. So sigma ij equals 0. And epsilon ij also equals 0. Because the displacement equals 0. No displacement. So because the epsilon is related to the displacement, right? We know that that's called kinematic equation. Epsilon ij equals 1/2 ui comma j plus uj comma I. Right, guys? So as a result, and the first one and the fifth one, this one, and they are equal to 0 also. That's the reason I only have the integration over, and this is the third segment. Right? The third segment is here. On the third segment, you can see the third segment. On third segment, and ui equals uiy, it is the function of y. Do you guys agree? ui with respect to x equals 0 because the x is fixed. Understand, guys? You can see it is a lot of fun here. Okay, as long as you select a very special this is the boundary gamma. Any questions regarding this one? dui dx equals 0 because x is fixed. X does not change. Easy. Are you okay with this one?
Yeah.
So because the x does not change, and because this line it is a vertical, x is horizontal, right? All these values on this vertical line does not change with your x, right? That means x, if you change x, the u is the same. That's the reason. So this derivative equals 0. And this equals 0, and that means this term and goes away. Or we only have w omega dy. So keep in mind, this is the third segment from minus h to h. Right? So this W is string energy density. And this is a string energy density. So this W, supposedly this W, it is independent upon y. That's the reason we take this W out. So this is 1x equals infinity. Very, very far away from here. How to get this W? And this is how we get this W for the linear elastic. So if you, hey Bobby, did you take the CAE with me?
No.
Nico, did you take CAE with me? Michael, did you take CAE with anybody? No? Or maybe CAE was cancelled before you before the times before the time that comes for you guys. Okay, I'm sorry if you cannot learn that one. So I just teach you here, or just draw this as a set, is a note here. How to calculate this omega, this energy density, and do the integration with sigma yy with respect to epsilon yy. This is 1D, okay? This is a 1D from 0 to epsilon yy. So this equals, for linear elastic, it equals 1/2 sigma yy epsilon yy. And for plastic, and yield strength multiplied by epsilon yy. So this is the J, okay? So this is how we can calculate the J. And also, I want to write you here. So this is a kinematic equation I told you guys, right? And you just draw down. You just underscore this one. This is called kinematic equations. It's a kinematic equation. Kinematic equation relates the strain onto the displacement. Questions? No questions? And so here is the infinite crack, and then we take a look at. So this is pure bending. Okay, so this is for pure bending. Also, and this origin is that, and this is the crack tip X and Y, and we also, but now this time is a pure bending, and practically pure bending does not exist. Okay, but only for educational purpose, we have pure bending. Because why? Because when you have any kind of bending, and you must fix something, fix some edge. Otherwise, you cannot have bending. Do you guys agree? Okay, so also we use select this is the rectangular shape. 1, 2, 3, 4, 5. For J, okay. I just skip all this integrand. And for 2 and 4, dy equals 0, right? But this is a pure bending, okay? Ti equals 0, no Ti, traction free. So as a result, integration on 2 and integration on 4 equals 0. And for the third one, so this third segment, and it's a stress-free, no stress, no strain. Okay, but on this edge, no stress, no strain. That means omega equals 0. Omega equals 0. Omega equals 0. That means the third integral is gone. You understand? Now we only have the first one and the fifth one. On the first one and fifth one, and how can we calculate the traction? And Tx equals sigma xx nx plus sigma yy ny, which equals sigma ij nj. Do you guys still remember this? Do you guys still remember? Do you guys still remember? This is T. How to calculate the Ti? Ti equals sigma ij nj. Right? So Ti for here, I will Tx. And x equals 1, and this one equals, and sigma, so this is T1 equals, and sigma 1, 1, N1 plus sigma 1, 2 multiplied by N2. So because some students, they are not familiar with this is the subscripts x and y. So this is x for 1, y for 2. So this one can be changed. So Tx equals here, Tx equals sigma xx multiplied by nx plus sigma xy multiplied by ny. Right? This is how we get here. And then we take a look at what is nx and ny. So for the fifth one and for the fifth one and the fourth one. So here is out of order unit model, normal, right? Out of order unit model is n equals -1, 0. Do you guys agree? Do you guys agree? Do you guys agree? Okay, so this is my nx. So this is my ny. And you just plug in. And Tx equals ny equals 0. This gone. And this n sigma xx and nx. Nx equals -1. This minus sigma xx. So this is how I get this sigma xx. Right? Make sense? Bobby.
Why is n -1 for pure bending?
Sigma y.
Why is n -1 nx? Why is it -1 for pure bending?
No, not necessarily pure bending, because this is edge. This is edge. So this x is y. Right? This I mean the n is the outward normal of this edge. Outward normal.
Oh, that's all that's not the force or?
No, for normal.
Oh,
Normal direction of your boundary. Okay? So this guys, look at me guys. So this is the boundary, right? This is the material, this is the boundary, this is air, right? You guys agree? So the n means the outward unit model, unit normal. N is the outward unit normal. So because this is x, this outward unit normal goes this way, that means -1 and 0. Questions so far? Questions? Okay, T2. What kind of T2 guys? So this is the T1, right? So this is so here. So this is Tx. So the Tx, then we have also on the y1 and the y on the first one segment and the fifth segment, guys. Because it is a straight line, okay? Because it is a straight line. You guys agree? Because it is a straight line, and the straight line means the arc is a straight line, right? That means the ds is negative to dy. Right? You understand this? And now you get so much, you are confused, I think. What is the arc? So this is the arc. Right? This arc, this is the ds. But now if I straighten this arc, I'm just straighten this guy this way. So the ds equals dy. So this is x and y. So this is y. So here is a dy, okay? So this is dy, this is ds. Keep in mind. So my gamma, the direction is going down, right? Otherwise, ds equals dy. If going on. My boundary, okay? My boundary is counterclockwise. Going down on line segment 1 to the right, going up, going to the left, and then going down again. That's the reason on these two segments, ds equals negative dy, because the direction is going down. As I said, and this gamma must be counterclockwise. Counterclockwise. If you go to clockwise, you will have a negative sign. Questions? So because dy equals ds, and j for the first segment and fifth segment, and we can just simplify, okay? We can just simplify this one, ti1 dux dy. This is a dy, right? And the T2 equals 0. T2 equals 0, guys. You can see, and T2 equals Ty. Sigma yx equals 0. We do not have that one. So we have So finally, we only have sigma xx here. The pure bending sigma yx equals 0. Okay, for pure bending. So this is our fifth segment, and this is our the first segment. And you can just put them together, and you have omega sigma xx exx, and then you just put it here. And this omega is a straight energy, okay? Straight energy density. Here I just draw this one, and this is epsilon, this is sigma, okay? So the W, this is curve. So suppose this is the curve. Underneath the curve is omega, straight energy density. However, above this curve, Q is called complementary energy density. If you have not taken CAE with me, please write this down, guys. Please write this down. So here is the epsilon, guys. You can see this is epsilon, this is sigma, and this is a curve. Underneath this curve, and we have omega. Above the curve, Q is called complementary energy density. So this guy's definition and the definition of omega, they are just opposite. Right? You understand? So W, this is Q, and W, and omega. Omega is defined as from 0 and to epsilon ij, sigma ij, d epsilon ij. So this is omega. W is defined as from 0 to sigma ij, and epsilon ij, and d sigma ij. So this is called the straight energy density. So this is a Q is called complementary straight energy density. So keeping this in mind. Any questions so far? Any questions so far? You can see epsilon xx multiplied by epsilon sigma xx multiplied by epsilon xx is just the area of the square. Right? The area of the square minus omega, which equals the area above this curve. So this is the curve, and how the strain changes with epsilon, and how the stress changes with the strain. Hey, by the way, guys, there is no the elastic CAE. What replacement courses are you taking now?
Was there machine design and
Machine design?
that was the replacement?
That's the only one. But machine design has been there for many years. There's no replacement.
I don't think.
Okay, but in the machine design, I taught machine design also. In the machine design, we did not go so deep. But in computer-aided engineering, actually computer-aided engineering, and we focus on the linear elasticity. So this gives us a lot of. Let me lay the foundation for you guys and to take other courses. But they just cut it off. Even though there's some similarities, something in common between the CAE and the machine design, but in my opinion, just the CAE still has its own value here. Any questions so far? So if you have not learned these things and just treat this one as a new thing, okay? This is new knowledge. You understand this? Does that make sense? My bottom line is that you know what they are and how to use these to do the calculations. I do not ask you guys to derive anything. Okay, and then we talk about, we cannot finish, but because this is very, very important. So in 1972, and Landis and this Bagley used multiple specimens to determine J, and how to use multiple the specimen. All right, how to use multiple specimen. You can see A1, A2, A3, A4. So this is the crack length. The crack length is changing. For different specimen, I suppose nominally these materials and they are the same. All these specimens, they are made of the same materials. But for each specimen, I have a crack length, different crack length. For each of these crack lengths, I do this. This is the delta. I calculate the displacement, the relationship between P and delta. Is the P and the delta. And then I can, for each of these crack lengths, I have the curve. Okay, guys? I have a curve. For vertical line is delta. This is a delta. And for here, for the U, and U is a potential, U is a spring energy density, right? Spring energy density. So you can calculate the U from different delta 1, delta 2, delta 3, and you will have this U here, du dA. And du dA actually is because we do not have external force here, and du dA equals d pi dA. Do you guys agree? Do you guys agree? The pi, let's see, pi equals U minus W. W equals 0. W equals 0. Why? Because the delta is the same. Delta does not change. U equals 0 because delta is 0. Then this is the d pi dA equals du dA. That's the reason from du dA, and you can get J here. But keep in mind, though this one is a slope, but we know and J equals negative d pi dA. There is a minus sign here. And that's the reason we have J is positive. Questions? Okay. And so here, so this is race, a proposed single specimen approach, and for this double-edged notch specimen. So this one is very, very expensive. To do these kind of things is very, very expensive. Then the race and did something differently. You can see this is a P, and I have a edge crack on this end, another edge crack on this end. The ligament is 2A. That means 2A plus 2B equals the total width. Right? So first tape, for the first tape, for the one tape, okay, one tape J, and this is what we have, and this is the displacement control. Delta is changed with crack length. Okay, which is this one, and the two tape, and we will have two tapes. So dA, okay, dA equals 2dA, and we assume the unit thickness. We have unit thickness. A is a crack tape. A is a crack area. So I'm going to stop here now, because currently our goal is to finish our the modeling part. After you finish modeling part, and I think that you guys will be very, very happy. We already have the kind calculation things. So you can just focus on this is the modeling part now. Okay, I'm going to stop here and next is Friday. I will email me the screenshots. And then you can just, we can just finish this one. Questions so far? No question? Hey, George, can give you a hard copy here, if you want. Okay, so if we can have not finished the modeling of that for the handout example, you need to give me let me know by this evening, okay? By this evening, show me you have already finished it.